watching Jaron and is that it? 1, 2, 3, 4. Okay, apparently I don't know all of you. Michael, Chad, and Michael, Chad, and Sally. I marked Sally here. The number that I marked present did not match the number of people I counted. Okay, let us review. So now Sally's here. So in preparation for exam 3, there are 3 different areas that you could have your calculus specific question. So I'm going to look at those 3 different areas and then, assuming we're all good, go on to some relativity ideas. If you want more discussion about the test before we do the relativity, ask questions, because I want to cover what you need before I move on to the things we need for the class. So the first area is to carry over what we covered just before the last exam. So the Maxwell's equations, remember we have 4 Maxwell's equations. Those equations are shown right here. And you should be able to combine these equations to show that it forms a wave equation. So the goal is to take the top 4 equations, using the one that is listed between them, and combining, get to the bottom one. So does anyone remember doing that? Excellent. Nose on the memories. Okay, so here's how we did it. We started with this equation here, and we did del cross on both sides. That was our first move. Our second move was to recognize that del cross anything, if I just solve it for that, I would have anything, so I'm going to put in the E, is equal to instead of A, I should have put E since I substituted in E, is equal to that minus del squared of E. So that's just using this equation. And so del dot E, I can substitute this for del dot E. And if I'm doing this in empty space, what is rho, the charge density in empty space? 0. So this is equal to 0 in empty space, or in vacuum.
If we give them another row, do we use that, or are we just not going to be given another row?
We're not going to be given another row. Yeah, we're not going to say, in some material that has a charge density that is non-zero, then derive it. That's not what we're going to do. So that's just going to become a 0. And then the del cross E is equal to what we have above. Well, from what we have above, since del is a positional derivative, I can move it inside the ddt because the positional derivative, partial derivatives with respect to position, aren't going to be affected by partial derivative with respect to time. So I'm going to put minus my d dt and then put the del cross B. I'm sorry, I'm totally blocking you, aren't I, Chad?
No, you're fine.
No, I'm fine. I just wanted to lay down. So doing everything that I've done, this minus d dt of del cross B is what my del cross E is. And then that's equal to the right side of the equation I had from above, minus del squared E. And now for the final coup de grace. We're going to take this equation and plug it in for del cross B. But if we're in empty space, there is no current density, there's no flowing charge, hence J is 0. And so plugging that in, I'm going to have, notice I had a minus sign on both sides. No need to keep the minus sign if it's on both sides. I can multiply both sides by minus 1. d dt of mu naught epsilon naught dE dt is equal to del squared E, or voila, d second E dt squared is equal to 1 over mu naught epsilon naught del squared E. And that is the wave equation that we were looking for.
Remind me how that's useful.
Remind me how that's useful. Okay, a very important question, not some trivial question. That is useful because anything that fits in this equation can produce a wave. And so Clerk Maxwell, in combining his 4 Maxwell's equations here, he realized that these equations fit the wave equation. Hence, electric and magnetic fields can produce electromagnetic waves. So the importance of this is it predicted that you could make electromagnetic waves. And furthermore, by matching the equation up, it predicted that the speed of the electromagnetic wave squared was equal to 1 over mu naught epsilon naught. Right, just from matching the positions. And so from that, he calculated the speed of an electromagnetic wave, and it turned out to be the same as the speed of light. And then he made the crazy assumption, or crazy jump in logic, to say that light must be an electromagnetic wave because it has the right speed. Which, in retrospect, was a pretty poor logical decision, but it was correct, nonetheless. So poor logic, but turned out to be right.
If we're given this kind of thing, will it be the derivation of it, or will it be...
You would be given 2 things you could get. One would be you could get these equations, basically what I have in that box, and be asked to show that this, forms a wave equation.
Would we also be given that little
Or-
del squared A equals...
Yeah, everything's in the box there. Or,
So the goal there would just be to get it down to what's in the black box at the bottom?
yes. Or you could be given something like, and say, show that this is a solution to the wave equation. And in that case, you would take this and you say, okay, let's take the second derivative with respect to time, and the second derivative with respect to position. Remember, del is just I hat d dx plus j hat d dy plus k hat d dz, which means that del squared, which is del dot del, is equal to d second dx squared plus d second dy squared plus d second dz squared. And so that's why I said the second derivative with respect to the spatial variable x there, because that's what the del squared is. So those are the 2 kinds of things that we could have with Maxwell's equations. Any other questions about that option?
Can you do that real quick?
Yeah, absolutely.
We just talked about that. It's a little confusing.
So let me take the second derivative of E with respect to time. So it's the derivative of the first derivative. Derivative cosine is going to be minus sine of omega t minus kx. And then times the derivative of the inside, which is going to be omega. Take the derivative of that. Derivative of sine is cosine. Times the derivative of the inside, which is again omega. Wait a minute. Yeah, that's right. So there's my second derivative with respect to time. Question?
Can you identify the variables?
The variables are time and position. So this is one variable, that's the other. Is that what you wanted? So then I do the second derivative with respect to position. And the derivative of the inside with respect to x. Go ahead.
Just negative k.
Yeah, negative k. Sorry. I moved it up so I don't have to write on the bottom, but then my hand makes it shift page. So it's plus k E0
Plus k squared.
Well, I'm doing the second derivative now. Right, because there's still a derivative that need to be done.
Oh, I see what you're saying.
Being at the edge of my tablet, I did not write very well. Okay, so now I have my second derivatives, and I put them into that form. And so putting them into the form, I'm going to have, so I just want to put them into this form right here. So I have the derivative with respect to time, which was minus omega squared E0 cosine of. So I'm going to put equal with a question mark because I'm testing to see if it works. C squared times minus k squared E0. So I take these and I say, E0 cosine omega t minus kx is common on both sides. So I can factor that out or divide it out for the cases where the cosine term is not 0. And I have minus omega squared equals minus k squared c squared. Well, that is true if c is equal to omega over k. K is actually called the wave number. In this case, it was, it's just the constant that I multiplied x by, right here, bottom of the screen. So that would be how I would test it. Okay, moving on to the second type that we could have. The brachistochrome problem as we applied it to Snell's law. That is, we used Fermat's principle that light travels from point A to point B in the path of least time, and then solved to find what path that would be, and in the end came up with Snell's law. So Snell's law is a result of Fermat's principle. Now, Fermat's principle was an idea when he proposed it, but it turns out that when you look at Huygens' principle, light actually follows that. So this one here, remember we found the time that it took in medium A, or medium 1, the time it took in medium 2. We added those up, so there's where it shows the equation. Time is equal to a squared plus x squared over v plus square root of v squared plus d minus x all squared over v prime being the speed in the second medium. And then we said, let's minimize this. How do you minimize something? You do what? Take the derivative and set the derivative equal to 0. Okay, so we took the derivative of that time equation and set the derivative equal to 0. And the derivative, as you see here, gave us these things that geometrically just turned out to be sine of the angles on each side. And so we made those substitutions. And then the final thing is using the definition of the index of refraction, the speed of light in vacuum over v, to substitute from v and v prime to n and n prime. Question, Michael?
That t equation, is that something that we're supposed to know, or is that going to be...
No, you just derive that by geometry. You are supposed to know that distance is equal to speed multiplied by time. And that's derived using distance equals speed multiplied by time. Okay.
So what will we need to know if this was on the test?
You would, well, yes. You would need to know the definition of sine. You would need to know the Pythagorean theorem. You would need to know that distance is equal speed multiplied by time. And how to minimize an equation. And then you have to put it all together. The putting it all together is the part that is the physics, right? The other stuff is just rote knowledge. That's not really what I care about.
So for the concepts there, obviously would be like, okay, we're singing for Matt, how do you pronounce that guy's name? Principal?
Fermat?
Yes. Would we also have to list that it's a recursive? Yeah, that kind of problem.
Well, you wouldn't have to know the word recursive.
Okay. Say that
And I would say Fermat's principle says that light takes the shortest path to go from point A to point B. Show that if Fermat's principle is correct, then Snell's law is an outcome. So, right, you don't have to know the name Fermat's principle or the word macrystochrome, which I looked up and nobody can agree how to pronounce it. Like, one said brachistochrome, another one brachistochrome, another one brachistochrome. Yeah, no one can. I'm sure there is a correct pronunciation, but... Okay, so this one here, of course, the definitions of sine and cosine and whatnot were necessary, and Pythagorean theorem just for the geometry parts.
Also, the equations that we'll have for the test, is that the same one that's listed on Moodle?
I need to make sure I go through and change variables because like U versus PE and K versus KE, but otherwise it should be the same. I will look and make sure that the microscope equation is the one that I used in class, which is magnification for a microscope is equal to
Will you maintain the labels that it has in regards to, because it has like the diffraction equation that says like this is constructive for this and destructive for this.
Yeah,
Will that make
yeah.
sense?
Okay, the last type of calculus question you could have is from Fraunhofer diffraction. And we only got through two types of Fraunhofer diffraction. We didn't get to the third, which is if you have a double slit. The true double slit is the product of the single slit and double slit derivations we did, because each single slit has its variation. So that part won't be there. But we did have these two parts that we talked about in class. So the first one was deriving the intensity equation as a function of viewing angle. Now in the general physics class, the 152 class, all we had was the condition for constructive interference and destructive interference. But here we have the intensity, so we see how the intensity varies with angle. How is that equation derived? Visually?
Graphically.
Definitions of things, I don't know.
Okay. It was derived by saying that the electric field going through each slit is going to be the same. And then taking that and saying, now when we get to a place on the screen, the electric field from each slit will be E0 cosine of omega t plus, and then we have the phase difference that's occurred, which would be the length times 2 pi radians over the wavelength. But you have two different lengths for the two different slits. And so you have, for slit 1, you have length 1, and for slit 2, you have that. And so if we have these two electric fields at the same location, how do we find the total electric field? We add them. Okay, as vectors is true, but we're assuming that we had a coherent wave, and so we'll just say, okay, they were in phase and they were pointing the same direction, so we don't have to say as vectors. But we have to add them. And so the E total at the screen is equal to the sum of these two and when you put it like this, it looks really ugly. I mean, because we just have these two big terms, and I want to try to combine them. And so that's where we have to use another trigonometric identity that says that when I add a cosine and a cosine, that this is equal to 2E0 cosine of the two things subtracted times sine of the two things added. Now, if I subtract them, the omega t subtract out. And I'm going to be left with just the two terms that had the L, and then it's divided by 2, so I better put over 2's. So subtracting them, it's going to be 2 pi over lambda times L1 minus L2. Adding them, it's going to be 2 omega t plus 2 pi over lambda L1 plus L2. And then we go from, so this next step is an important base piece of information. The intensity of the light is proportional to the electric field squared. So since intensity is proportional to electric field squared, the intensity is proportional to 4E0 squared cosine squared of, notice 2 pi divided by 2 is pi, so I can get rid of that over 2 and just make it pi So that's my intensity as a function of time. If I look at that as a function of time, the first term, 4e0 squared, that's constant. The second one, the cosine squared, that's constant. The third one, the sine squared, that's varying between 0 and 1. And the average, we said, was 1/2 because of the symmetry. And so this becomes one half. So my intensity average is equal to, and I'm just going to put intensity 0, which is just the peak intensity, cosine squared pi over lambda L1 minus L2. So that's a correct equation, but it's not the one shown at the top of the screen, right? Okay, almost can see them both. You can basically see because it's just cut off the last part. So what's the last step? The last step is finding the difference in the path lengths. And so for the difference in the path lengths, we come back up to this picture. And if we're in the Fraunhofer region, the far field region, then we have this magical 90-90-0 triangle. And we just cut it off so we have these 9 degrees. And this distance here is going to be delta L, or L.
Where are you, right? Oh.
L2 minus L1 is delta L. Now, it doesn't matter if it's L1 minus L2 or L2 minus L1. You get a minus sign, but in cosine, it doesn't matter. Right? Cosine of minus 5 is the same as cosine of plus 5. So it doesn't matter which side you're on, in other words. And so just using, trigonometry, we have the separation D, and the angle theta tells us this delta L is d sine theta. So that's the last step. This delta L is d sine theta. So there I put it in parentheses so it was clear where I substituted. And so that's the double slit derivation. Yes, I can. Now, the single slit derivation is taking these ideas but going to a continuous range. If we have a continuous range and we have to add the electric fields from a continuous range, that is an integral. And how do we do our integral? Graphically. We did the graphical integral by breaking this up into an infinite number of really tiny slits, with each slit having an E0 cosine of omega t plus 2 pi path length over wavelength. But that path length is different for each one of those little imaginary slits. And then we made phase vectors to add them up. And so this picture is illustrating making those phase vectors so that if you add up along the arc, okay, change it like this because you can see that. If you add up along the arc, you get the total electric field that went through the one slit. And if you add up as vectors going from the starting point to the ending point, you get the total electric field when you add up all of those phase vectors at the screen.
Wait, can you say that again? Sorry.
Okay, the total when you add up the length along the arc is going to be the total electric field that went through the slit. And when you add up the total from beginning to ending, that's the total intensity, or excuse me, the total electric field when you add up all of the different phases when you get to the screen. And so then we did the geometric integration. We have a graphic here, or not geographic, but a graphical integration, because we have this graphic to illustrate what the integrals are. And then we say, well, for a circle, I know things like, for instance, the arc length is equal to the radius multiplied by the angle of the arc. And for the straight line, the one that's labeled there as A with a vector, I could use a right triangle that covers half of that and relate tangent of the angle to, or excuse me, not tangent. This side here is radius, so I want that side and this side. So this side is opposite, this side is hypotenuse, so that's sine of this half angle with half of this. And then I can get equations that relate the radius to the total electric field seen on the screen and the radius to the total electric field that went through the slit. And since I have those two equations for radius, I combine them to eliminate radius, and I get an equation that gives me the electric field at the slit as a function of the the electric field at the screen as a function of the electric field at the slit.
So how do we get that original drawing graph thing?
This one right here,
I meant the other one.
this one here,
Yes.
that is, well, in practice, it's always more of a symbolic than a real, because we don't draw the graphical integration for a specific problem, we draw it for a general idea.
Okay.
And so we start off by simply saying, if I had a slit that went through some angle, and so it depends on what the angle is, what that picture would look like, and that's where we don't make it for a specific angle, we just say some angle.
Okay.
Then it would look like this. And then we use our geometry and trig skills to find from this picture that illustrates what it would be for some random angle, what the relationship is for any angle between the electric field at the screen and the electric field of the slit. And once we have the electric field of the screen as a function of the electric field of the slit, we just square, because intensity is proportional to the electric field squared. And that's what gives us the equation here for the intensity as a function of angle. Now, this is a more complicated function, right? It's very simple to see that the numerator is going to be 0 anytime that pi a over lambda sine theta is an integer multiple of pi. Right? Because sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, and so on. So we can see where we're going to have the minima very easily. How would we find where we're going to have the maxima?
Can you scroll down again real quick? For the average stuff?
You're still working on the...
Just trying to get it.
Okay. Given that equation, the maximum is not simple because we have theta on top and bottom. And so the intensity depends on both of those terms. We can't just say when the top is a maximum. Can I change back now, Chad?
20 more seconds.
Oh, wait. With that intensity equation, we found the zeros because only when the top is 0, the whole thing's 0. But for maxima, we can't just say when the top is a maximum because the bottom is also changing with theta. So if I go to that equation, you can see that sine of pi over 2 is 1, right? And sine of 3 pi over 2 is minus 1. Well, you square it and it's still back to 1. So those would be maxima for the numerator, but the denominator is changing with theta as well. And so if I have something that has both the numerator and denominator involved, I have to go to our normal calculus method. How do we find the maximum for an equation? Take the derivative and set it equal to 0. That will give us either the minima or the maximum.
And that's dd theta, right?
Right, it'll be dd theta. So when you do that calculation, you're going to find, well, let's just look at it real quick. Oops.
What was A again in that equation?
A is the width of the slit. So we have that equation, and we want to find maxima so we take the derivative at theta m, the theta that's going to be a maximum or minimum, and set it equal to 0. So I take the derivative of that equation. What's the derivative of this equation at the top of the screen? We're going to have to use a few rules, right? What's the first one? The first one's the easy one. Chain rule, that's the first one. So I'm going to move this over here just to give myself a little more space. I still probably won't fit. So using the chain rule, I have 2
Where'd the I sub 0 go?
What was that?
Where'd the I sub naught go?
I didn't write it because I wasn't thinking.
Just making sure.
It's going to drop out because everything is multiplied by it, but right, since it's equal to 0. But still, to be accurate. So then I have to do it times the derivative of the inside. Now what do I use?
Use
The quotient rule.
quotient rule.
The quotient rule, which the truth is I never memorized the quotient rule. I only memorized the product rule, and I used the product rule for these as well.
We'll just call it a negative thing.
Yeah. Who remembers the quotient rule?
I don't remember which way the top goes, so.
Okay, so we'll do it the way I remember. So I'm going to have, my two functions will be the top and the bottom, right, 1 over sine. I can bring out the 1 over a pi over lambda. That's not a very good nice lambda, because that's going to be in everything. And then I have derivative of the first times the second, so derivative of sine, cosine, all, but I have to use the chain rule.
Wouldn't that just be lambda over a pi?
What was that?
You wrote 1 over a pi over lambda, next be lambda over a pi.
Yeah, I could write that way. That would be another way of writing it. Like that. So derivative of the inside is a pi over lambda cosine of theta.
I know the second.
Woohoo! And then we have times the second, which is over sine theta. And then we have plus the first times the derivative of the second. Derivative of 1 over sine theta is going to be minus 1 over sine theta squared times derivative of sine theta, which is cosine theta. There you have it. And we want to set this equal to 0.
All the constants.
So, yes. Instead of dropping them out accidentally, we'll cancel them out intentionally. We will divide out everything that's a constant. So we divide out the I0, divide out the 2, divide out the a pi over lambda, divide out the pi over, or lambda over a pi. And we're left with still a crazy equation, right?
Yes.
Where are you
Just everything that is a constant I can divide on both sides and not have a problem. I forgot to put M's everywhere. Why what?
Why did you cancel a pi over lambda and over?
Because I just divided it all out.
To where?
I did 0 divided by that and it disappeared. Okay, I divide both sides by I0, and so 0 divided by I0 is still 0. And then I divide by 2, 0 divided by 2 is still 0. Then I divided by lambda, so 0 divided by lambda, still 0. Multiply by a pi, still 0. Multiply by a pi, still 0. Divided by lambda again, still 0. Remember,
Right.
this
Well, I
0.
understand what you did, yeah.
Okay, so now I'm factoring things out. What conditions will make that equation equal 0? What conditions? What situations?
If cosine of theta is 0. Right?
If cosine of theta is 0?
Sine of theta is 0.
Look at 0 minus 0. Okay.
Actually, I do have cosine theta m everywhere.
Well, at the very beginning, sine theta m.
Yeah, that's the one I was looking at. Cosine theta m. Yes, that is true. Okay, so let's list the conditions that will make this 0. Condition 1, sine of a pi over lambda sine theta m equals 0, which gives me a pi over lambda sine theta m is equal to an integer multiple of pi. Or in other words, a sine theta m is equal to m lambda. Well, we had already determined that's the situation that's going to give us the minima, because that's when we have 0 on the top of our equation. So we already knew that one gave us minima. Condition 2. I'm going to go for easy. Cosine theta m equals 0, which means theta m equals plus or minus pi. Well, sure, because that's the limit. That was just the limit. That doesn't help me at all. Condition 3. 1 over sine squared theta equals 0. How do I get the sine squared theta? Take one of these out and one of these out and bring it out here. Well, when is that satisfied? Never. Right? So that gives me no useful solution. And then I'm left with the one that I've been trying to avoid. When cosine of a pi over lambda sine theta m times a pi over lambda times cosine theta m. Oh wait, no, I already brought out the cosine theta m's, didn't I? Yes, thank you. Equals sine of a pi over lambda sine theta m over sine theta m. Now that condition, that's not a fun condition. I believe we solved this one as a transcendental equation.
What's a transcendental equation?
A transcendental equation is an equation that you cannot solve analytically.
Awesome.
Yes.
Great.
So,
test.
so for this, what you would do is you'd say, well, let's bring this over here and say, or actually, let's bring the cosine over and then the sine theta m up. So we have sine theta m is equal to a pi over lambda sine theta m is equal to tangent of a pi sine theta m over lambda. My handwriting is getting more and more sloppy, I think. This is a transcendental equation. You can't solve it analytically. What you do is you just say, okay, let's define a variable. We will say that this variable is x. This whole thing is x. And so the equation becomes x equals tangent of x. And then we plot as a function of x. We'll plot x, so that'll just be a straight line. And we plot the tangent of x. And the places where they intersect, that's where you have the minima. Or the maxima. It will come as no surprise that no general physics book has an equation for the maxima, right? Because it's really complicated, but that's how you do it. Now, there's one more thing that you can do with these equations.
Get lots of points for trying.
Get lots of points for trying. Yes, yes. One more thing is, what about the situation when theta equals 0? What do you have for, well, if we look at the the solutions that we just found, this solution said we have a minimum when theta is 0. This solution here says we have, these are for maxima. This one says we have a maximum when theta is 0. Is it possible to have a minimum and maximum in the same place?
I assume not.
Only if it's constant, right? So we need to determine which one is it. And we can see where the problem arises by looking at this equation. If theta is 0, what do you have in parentheses? If theta is 0, what's in that parenthesis that's squared?
Which side are you looking?
For the single slit diffraction. Sine of 0 is 0.
Okay, so you get 1 over infinity is, well, something.
No,
something
no.
over infinity over infinity.
Okay, sine of 0 is 0,
Oh, wait, no. 0
which
is
means that you have sine of 0 on top. So 0.
0 over 0.
On bottom, you have 0. So you have 0 over 0. Well, how do you find the value of 0 over 0? L'Hopital's rule. So you can apply L'Hopital's rule. I'm out of time now. Clearly, we're not going to cover the next material. But you can apply L'Hopital's rule then to find if it's a maximum or a minimum at theta 0. And that's where I actually ended the last class period. If you look at the notes from the last class period, that's the last thing on the notes. I was starting it. We ran out of time. I finished it and uploaded the notes. Okay, we're out of time. I'll see you at test time.